Please welcome OFC General Chair Jorg Peter Elbers from ADVA Optical Networking.
Good morning, everybody here in sunny San Diego. On behalf of the IEEE Communication Society, the IEEE Photonics Society, and the Optical Society, I welcome all of you at OFC, the world's premier event on optical communication. It's my pleasure to kick off our program today, and on behalf of my co-chairs, Gabriela Bosco from Politecnico di Torino, Lorraine Charles from IBM, and myself, thank you for being here and making OFC 2019 a truly memorable experience. Since I first attended OFC, I've returned every year, and it really feels like a homecoming to me. As a young PhD student, I was in awe meeting luminaries from industry and academia, and I see a lot of them here in the rows, whose papers I had read, and I was excited to find they were easy to talk to and happy to give advice. This has not changed since then. This world of more than 15,000 really feels like a community to me. It's always great to meet with peers and friends from all over the globe and to connect with new colleagues. This week, we have come together again to explore the latest and greatest in optical communications and networking. From the realization of 5G over expanded efficiencies in data centers to our role in the development of the Internet of Things, OFC offers the opportunity to push the limits of technology and to shape the future of our industry. That concept becomes clear if we do not only look at the more than 700 presentations that are given at the conference, but also at all of the innovation featured in the exhibition. With more than 700 exhibitors, no other event offers such an array of opportunities across the entire value chain. Thank you to all of our exhibitors and sponsors for helping to make OFC the world's leading show for optical communication. The exhibition opens immediately after the session downstairs, so head down and check it out. Even better, head down, stop by, chat with the exhibitors you want to see, and set up a time for a meeting before the show floor closes on Thursday at 4 p.m. An event of this magnitude takes a host of individuals to make the program a reality. I would like to thank the OSA staff and all of the OFC 2019 committee members and volunteers, overall more than 200 individuals. I'd also like to extend a very special thank you to our amazing technical program chairs, Pu Dong from Nokia Bell Labs, Junichi Kani from NTT Labs, and Chongqing Xie from Alibaba. Here they are. Please join me in thanking them for all their hard work and dedication. We have an excited plenary session prepared for you this morning with our speakers delving into some of the hottest topics in the industry today. And without further ado, it's my great pleasure to introduce you to Dr. Alex Jinsang Choi. Alex is Senior Vice President of Strategy and Technology Innovation, Head of Laboratories Innovation, and member of the Technology and Innovation Management Board at Deutsche Telekom in Germany. Prior to joining Deutsche Telekom, he served as Chief Technology Officer and Head of the Corporate R&D Department and the Technology Strategy Office at SK Telecom in South Korea. Before SK Telecom, he held various management positions at LG Electronics. Alex has more than 20 years of experience in the mobile telecommunications industry and was responsible for the implementation of the first commercial 3G network in Korea. Today, he will discuss how internet growth and the dawn of 5G will bring new requirements to optical networks. He will ask us to rethink the way networks will be architected and built in the future, and he will look into the shift towards disaggregation and open platform innovation. Please join me in welcoming Alex Choi.
Thank you, Jorg, for your kind introduction. It's such a nice weather outside. Good morning, ladies and gentlemen. It's really my pleasure to be here today at OFC conference. I really thank OFC for that. As briefly introduced, I moved from South Korea to Germany about 1.5 years ago to join Deutsche Telekom. This career change is very unusual because there was no previous case of South Korean working for the major international operators at executive level. I think I'm very, very fortunate. So my presentation is about open innovation in 5G. So let me begin by saying a few words about my company, Deutsche Telekom, or DT in short. Currently, DT is operating in more than 50 countries worldwide with 75 billion euro revenue last year. We have about 168 million mobile customers and 28 million fixed network lines and 19 million broadband customers. Total number of employees worldwide is about 217,000. We own extended fiber backbone in our European footprint. We have been pushing very hard our fiber rollout, particularly in Germany. Our IP migration has been completed in 5 EU netcos already. We have won all relevant public network tests, such as Connect, P3, Open Signal in our footprint. Last but not least, we drive network innovation with 5G and edge computing. So 5G gets a rear for DT this year. Depending on spectrum auction result, we will start to roll out 5G network in our European markets from this year as part of capacity and speed enhancement, starting in selected areas such as cities and campus networks. The first 5G deployment will be as an overlay network on 4G based on non-standalone standard. To ensure a great user experience from the get-go, our focus now is on readiness. The whole end-to-end chain will be impacted from terminals across radio, transport, core to the related IT systems. Regarding 5G economic rationale, our belief is 5G will be more efficient than 4G from 2021 onwards. Also, 5G will enable new revenue streams in selected areas such as massive IoT, low latency connectivity service, and campus networks. 5G can also be a good option for fixed wireless access. 5G will enable new services such as assisted automated driving, new AR solutions, Industry 4.0 applications like remote robot control, massive video distribution, immersive contents, asset tracking, connected drone, and etc. 5G operators need to take care of following 5 technical challenges to make their 5G services as common use cases. So let's dive into. I will go from left to right. First, exponential traffic growth. As mentioned by many professional organizations, including Cisco, traffic growth will reach 5 zettabytes per year by 2022, based on the current annual growth rate of 25%. Zetta is a 10 to the power of 21. That's enormous. What's more complicated is that the busy hour traffic increases even faster than the average traffic. The video traffic played a major role on such increase. The problem is that operators' ARPU does not increase on par to the traffic growth, which creates a gap that must be closed with new technologies. Second is the total investment cost for the 5G radio access network. 5G uses high-frequency band like a 3.5 gigahertz on top of existing bands compared to 4G to secure broader spectrum range. As a result, 5G requires a larger number of base station antennas to match the service quality, which is a giant cost by itself. Adopting a more open and standardized base station can be a solution by increasing economies of scale and by better accommodating the innovative technologies for cost reduction. Third is front haul and back haul for 5G. I'm sure this is a topic that all of us in this room are very much interested in. Currently, 3GPP offers diverse options for splitting the baseband processing between the RU and DU. All of these options create different front-haul requirements, resulting in a wider range of front-haul options than 4G LTE. Operators thus can choose the best options according to their 5G network rollout strategy. Such flexibility is no doubt desirable, but it can also complicate the operator's 5G network operation, which creates needs for automation tools to solve the problems. Fourth element is energy efficiency. 5G uses diverse active array antennas such as massive MIMO, which increase energy usage. Increased energy usage is a burden on the operator's 5G network OpEx. Any creative solution for energy efficiency of resources would be more than welcome. The last but not least is a service deployment flexibility. As you know well, the agile service development environment, such as DevOps, is the trend on cloud-based IT infrastructure. On the other hand, similar efforts by the operators, such as the service virtualization efforts, are still far behind. In other words, the delay between new service requests and the actual delivery is much longer for operator services, resulting in the low service competitiveness. Therefore, operators need to accelerate the execution of service virtualization and develop technologies that can free from the legacy systems. This slide a little bit busy. This slide speaks of technical challenges from a different point of view. In addition, it contains the key issues in the mid to long-term viewpoint of operators. Let's start with the network diagram consisting of five layers on the left. As shown, the network consists of, from the bottom, access layer, IP layer, cloud and service platform layer, and control orchestration layer, which can form virtual networks on a global scale. At the top of the figure is the custom interaction and product layer. A close look at the picture shows that there is a colored border in each layer, which indicates that the physical infrastructure coverage of operators are limited in reality. First, let's look at the very bottom layer, which is the access layer. This layer includes all of fixed mobile, cable, FTTH that you all are already familiar with. As we will see later, this is a recent disassembly of data plane and control plane for RAN virtualization, and also softwareization and network flexibility through SDN and NFV technology and unification of different access technologies are really happening now. In particular, lambda switching or wavelength switching technologies are increasingly expanding from existing IP backbone and backhaul to the front haul of metro and mobile networks. The reconfiguration, programming, and automation on lambda levels, known as photonic fabrics, will be an essential feature in 5G. Second is the IP layer. This part corresponds to the network of current IP routers and is the area where IP packets are switched according to the various IP routing protocols defined by IETF. Especially as the SD-WAN, software-defined WAN technology, and the related markets are gradually expanding, innovation in the IP routing technology is expected, which will evolve into a more open layer in the future. Third and fourth layers are the cloud and service platform layer and the control and orchestration layer. These layers can be seen as the focus of development and operation of all telecommunication services of the future, as the operator network is gradually being virtualized. All legacy data services and IP-based voice messaging services are made right here, including low latency video services. In other words, these layers are the most essential platform for all service providers, including operators, and will cause the most intense competition in the future. These are the so-called OTT layer, where it's allowed to access to neighboring markets without physical access infrastructure, thanks to virtualization and software-defined network technologies. The concept of network slicing in 5G will also be realized through this layer. However, due mainly to the lack of the final version of 5G standalone core network standard, we would need to wait a little bit more for the commercialization of real, true network slicing. Now, let's have a look at the right-hand side, the billion-dollar questions to our 5G ecosystem. Number one, how do you see the value chain development in the different layers? Number two, where do you see global operators' right to play? Number three, what are the key technology enablers? And number four, where do you see your value add? We have the answers to some of these questions, but all these questions require constant considerations by all stakeholders in the ecosystem, including us. In this sense, rather than discussing the detailed answers to these questions right here today, I recommend you all to take these questions home and ponder for answers. Now, let's talk about the importance of openness in communications and networks, and the importance of orchestration, which further links each building block from the left to the right. Based on the necessity aspect, openness is inevitable if we take into consideration the communication network itself and the various current and future services running on top, as well as industry-wide ecosystem related to the network. The problem is how open we will be and who will standardize the interfaces. Setting up the reference architecture and standardizing the physical or logical interfaces for each building block, for example, by 3GPP or broadband forum or any other standard forum, is never enough. The contribution of open source community for actual implementation is crucial. Let's take a moment to review the shipping container industry shown in this slide. In our industry, containerization refers to actually the virtualization software technologies, not the shipping container. But let me use this shipping container industry as an example. They are different, but at the same time, they have something in common. The history of shipping containers is as follows. In the pre-1970s, before the container was standardized, half of the transportation cost consists of the simple labor cost. Many ports laborers spent a long time on loading various types of cargo. Such cost structure eventually hindered the growth of the whole shipping market. Once such a problem was cleared, thanks to the invention of a uniform, open standard shipping container in the 1970s, the entire shipping market enjoyed a rapid growth with the economy of scale these containers brought to the market. In other words, this is a great success case of standardization and openness leading to the market growth. The telecom and the network markets are standing on the verge of the inflection point with a sizable momentum. The decisions we take to accelerate it will determine whether it will bring success to both the market and the ecosystem. Good news is that various efforts are now being made throughout the ecosystem. On the right-hand side, I put the list of the organizations. They are the industry alliances working on such efforts. However, there is still a long way to go beyond the standardization stage, as the 5G needs to be deeply applied to telecommunication and network in earnest. To do so, we must overcome the final barrier of commercializations. A harmonization among these various industry alliances is critical. A mutually productive competition is desirable, but there is a need for a close collaboration to prevent confusion in the market. In addition, various forms of co-work between existing traditional vendors and startups armed with innovative ideas are essential. This is the final point that I would like to strongly insist today. Having said, let's deep dive some of these key open alliance activities. First, ORAN, or Open RAN. This alliance is newly founded last year after the merger between global X-RAN and the C-RAN, or Cloud RAN, in China. Deutsche Telekom is one of the founders of ORAN, and personally, I'm working here as a COO. Currently, we have 19 major operators worldwide, including Deutsche Telekom, AT&T, Verizon, Orange, Telecom Italia, China Mobile, China Telecom, major South Korean, Japanese, and Indian operators. We recently published our first ORAN specification in area of front haul. Moreover, ORAN successfully showcased 6 different use case demos at Mobile World Congress last week. This demo includes implementation of radio intelligent controller load balancing, AI-powered user quality of experience, programmable millimeter wave white box radio unit, and often front haul interface implementation, which are sponsored by Verizon, Docomo, SK Telecom, my former company, and etc. ORAN is also closely collaborating with the Linux Foundation networking community for their open source implementation support. This is a great achievement so far, and we are excited to see more throughout this year. The second, Telecom Infra Project, or TIP in short, sponsored by Facebook. TIP has been making efforts in various network areas to accelerate innovation and ultimately help operators provide better connectivity. One of their key achievements is open optical line systems, as shown in this slide. Another big achievement within TIP community is millimeter wave-based wireless networking solutions for operators called Telegraph. Actually, we call this project a virtual fiber in DT, and we co-led this innovation together with Facebook. We have already done 2 field trials in one of our DT European market, which is Hungary. The 2 field trial sites are Mikebuta and Marko, and the trial result are very encouraging. Particularly, we shortened the time to roll out dramatically by agile way of project execution. This is a great example of how our industry should work together in executing joint innovation. To know more about this, let me show you a 3-minute video.
Telegraph, it's a technology which is helping Magyar Telekom to reach customers with a fiber-like connectivity without digging.
You know, you want a fiber going through a street, right? You have to interrupt the traffic, stretch the cables.
That could take years if you want to connect a complete city. This is what we call virtual fiber. It's fiber, but it's virtual because it's in the air.
Connectivity is a complex problem. I don't think any single company can solve it. We have done everything that we wanted to do in our campus, and now it's time to go out and work with partners to deploy this technology.
Mivel ugye egy internetvonalunk van, és azért 3-4 gép is megy egyszerre, így nagyon-nagyon nehézkes.
This is something which was long tested, and now we are actually proving that this can work.
The major point is how fast you can get your service up and running. Deploying Telegraph is very fast.
We turned the switch on and we connected the first user, which is Mayor's office, and we could boot up.
They literally deployed a network in 6 days.
That was the moment where I became convinced that Telegraph is a good approach.
We want to see Telegraph scale in large cities, in large suburbs.
It's a very clever idea because it provides more flexibility for a rollout so that you can be more demand-driven.
You can build a smaller scale network at first, and if you have enough market interest later, you can add Telegraph nodes off to the side.
I see the city with different eyes. Wherever I go, I look up, for example, would it be possible to mount an antenna on this lamppost?
This is something that everyone should have access to. And it just feels great to give this experience to everybody.
Once again, the customer feedbacks after our trial was really, really great. And I'm so proud of my team led by Dr. Andrea Gladish for making this happen. The next one is ONF, Open Networking Foundation, and CORD, Central Office Re-architected as a data center. Access 4.0 is our DT internal project name for this particular fixed broadband access network use case. We built a cost-efficient access edge out of open commoditized hardware as well as open community software. The design is based on ONF SEBA, SDN-enabled broadband access, a lightweight platform based on ONF Verta. It supports a multitude of virtualized access technologies at the edge of the carrier network. I'm not going to get to the details here. Last but not least is edge cloud computing. I'd like to spend a few minutes to explain about the status of this project and the ecosystem on edge cloud platform, which draws keen interest from operators and is quite different from existing open alliances such as Orange. Deutsche Telekom is leading the edge cloud ecosystem developments with the several companies in this field. For example, in last week Mobile World Congress, we DT hosted a demonstration of a multiplayer AR, augmented reality game with the DT Cloud IaaS infra in Germany, and to demonstrate the success of the edge cloud in the consumer gaming market, along with major partners such as Niantic, the AR game company famous for Pokemon Go, Samsung Electronics, the mobile device market leader, and the Mobile Edge, a startup founded by DT in Silicon Valley to provide edge platform software. The role of Mobile Edge, the newly founded company which develops the edge platform software, was essentially important for cooperation between these four companies. As is shown in this picture, Mobile Edge plays a role of connecting cloud providers, technology partners, app developer, and device makers. The emergence of edge cloud is a prelude to the edge infrastructure located between the device and the central cloud, enabling various computing requirements and low latency services of various devices, especially mobile or IoT devices required by 5G. So far, I have covered various aspects of open ecosystem around 5G. In conclusion, 5G is leading the convergence between industries and markets beyond the existing scope. Doing so requires new openness-based standard and ecosystem to guide and promote the integrations. However, I must admit there are many barriers to overcome to achieve the rosy picture I just explained. So I wish all of you could play major roles in leading these open innovations. That closes my presentation. Thank you.
Thank you, Alex, for this inspiring talk. You just confirmed that 5G and open platform innovation and edge computing are very hot topics in networking indeed. I'm sure we'll have many more discussions around these here at the conference. Good morning, everyone. My name is Lauren Cheris, and I'm one of the general chairs for OFC this year. This morning, I have the privilege of introducing this year's award winners of the co-sponsoring societies. Today, we are recognizing these individuals for outstanding achievements in their respective fields. These awards and honors will be presented later today by the IEEE Communication Society, the IEEE Photonics Society, and the Optical Society during a special awards ceremony luncheon, which is supported by Corning. Let's take a closer look at everyone being honored today. We are fortunate to have many of those honorees in the audience today. Will all of today's award winners please stand? And please join me in congratulating all of this year's award recipients. It's an honor to host this crowd of exceptional individuals who are addressing today's most important topics in optical communications. And throughout the conference, you'll notice timely sessions address some of today's hottest developments. For example, consider our Data Center Summit and Network Operator Summit on the show floor. They feature talks from David Temkin, Vice President of Networks at Netflix. He will speak today on the evolution of content delivery. And tomorrow at the Network Operator Summit, Genia Wilburn, a Senior Vice President of Global Network Operations and Assurance at Verizon, will expand on the fiber build-outs and their impact on 5G. Speaking of today's hottest topics, it is my great pleasure to introduce our second plenary talk from Dr. Benny Mikkelsen. Benny could be called a serial entrepreneur. He is the founder and chief technology officer of Acacia Communications, a successful startup focusing on coherent optical interconnect solutions. Prior to joining Acacia, Benny co-founded Mintera and served as vice president of technology. And before that, he held various engineering roles at Bell Labs. Benny has published more than 200 papers. He holds a master and a PhD in electrical engineering from the Technical University of Denmark. Benny's talk focuses on photonic integration and digital signal processing. These are key technologies to support ever-increasing need for higher data rates and smaller, more cost-effective optical modules. Benny will provide an outlook on the challenges and opportunities the industry is facing and how co-packaging of optics and electronics. Please welcome Benny Mikkelsen.
Thank you very much for the kind introduction. And thank you very much to OFC for inviting me to give this presentation. It's a true honor. I believe this is my 32nd OFC in a row, so being here as a speaker is truly an honor. As the title of my presentation suggests, I'm going to discuss how electrophotonic integration can help tackle capacity and density challenges in optical network. In particular, we're going to discuss how photonic integration can help in transport, how it can help in short-reach applications, and even how it can help bringing bits in and out of switches in a cost-effective and power-efficient manner. But let's first discuss some of the key drivers behind the increase in capacity and density requirements. And as you probably all know, more users, more devices get connected every day, requiring higher and higher speeds, and also we consume more and more video content everywhere globally. And on the horizon, we have new services like self-driving cars, we have augmented reality, we have healthcare, and we have Internet of Things coming, increasing further demand for capacity as we go forward. And also, there are several reports showing that capacity roughly grows between 25% and 30% year over year. And also, there are several reports showing that network operators spend roughly 7% more on capital equipment on networking year over year. On the optical transport segment, roughly 3% get spent more every year. And on optical transceivers themselves, roughly 10% increase year over year in sales. So the good news here is we get paid more and more every year. However, the challenge is traffic is growing even faster. So innovation has to bridge that gap between what we get paid for and what we have to deliver. And electrophotonic integration is certainly key to achieving that. Also important to notice that the total cost of ownership is not just the cost of the equipment, but also the cost of operating the equipment. And part of operating the equipment is the cost of space, the cost of cooling, and also the cost of supplying electricity and power. And there are some forecasts predicting that in 10 years, actually 20% of the global electricity is going to be consumed by information technology, in particular consumed by data centers and wide access network. So obviously on a high level, there's a strong interest in decreasing power consumption of telecom equipment. Also, if you look at it more in a, so to speak, localized, inside a data center or central office, if the equipment is consuming too much power, you can have hot spots, meaning you can have half-empty equipment. And as we scale capacity, and if we don't take care of power consumption at the same time, we could end up in a quite unfortunate situation. So clearly we need to also take care of power consumption as we scale capacity. And fortunately, integration, our history has shown that integration is a very, very powerful way of not just increasing capacity, but also at the same time reduce size, power, and cost. For example, 60 years ago, we had the world's first computer. It was quite limited in processing power, took up the space of an apartment, consumed an enormous amount of power, and was quite expensive. Whereas today, we can get an iPhone, do many, many more times of processing, very power efficient and actually affordable at the same time. So integration has shown to us we can increase capacity while at the same time we reduce size, power, and cost. So how does this apply to optical networking? Well, when we talk about optical networks, we really have two key components, right? We have electronics and we have photonics. Let's start by looking at the electronics first. So in the electronic domain, we have Moore's law, meaning we have a generic building block, meaning a transistor that shrinks on a pretty consistent time frame. Every time we go into a new CMOS node, we get a smaller transistor, meaning we can integrate more and more of these transistors onto an ASIC. As a matter of fact, today, we can integrate billions of transistors onto a single ASIC. And we believe this Moore's law will continue for quite some time. We are, however, changing transistors. In old days, we used planar transistors. Now we're going to FinFET, and going beyond 3 nanometers, we might see a new type of transistors. But we believe Moore's law will continue for quite some time. Going to the optics side, we cannot yet integrate billions of optics functions. We can integrate hundreds of functions, shown here by some pioneering work by Luxtera on silicon photonic and Infineon on indium phosphide. One of the challenges we have in the photonic domain is that we don't have a single building block, right? We need to both build lasers, modulators, receivers, and splitters, etc. So there are many, so to speak, different building blocks. And also we don't have a common material system like CMOS. And also we don't have this dimensional scaling working for, so to speak, the electronic guys. We are limited by the wavelength of light, so we cannot truly shrink things arbitrarily small. So the net of all this is we really don't have a Moore's law for optics. So what that really means is that optical engineers have actually to be more creative than the electronic colleagues. And as you'll see later on, they are actually doing a very, very great job, as you'll see later on. So how do we integrate electronic and photonic? Well, there are really two main concepts you can do. Monolithic integration, where you integrate electronics and photonics in a single process, typically silicon. And there are some examples here to the right, showing some early work and pioneering examples. The other approach is to do heterogeneous or co-packaging, in which case we can either take the photonic and electronic, put them on a common substrate, we call that 2D, or we can put them on an interposer, and we call that 2.5D, or we can start stacking them, in which case we call it 3D integration. And again, here to the right, there are some early interesting examples of how we have done that. In the coming slides, we're going to show more details on or examples of how we integrate electronics and photonics. So how can optical networking benefit from electrophotonic integration? Or put differently, how can such a network as shown here, where we have front haul, back haul, metro, long haul, subsea, we have a data center part of a network where we have data center interconnect, campus, you might have a data center where we have racks of servers, and we have, assuming a leaf spine switch architect inside the data center. How can we, so to speak, optimize capacity of that network while at the same time reduce cost? Well, if Shannon could call Moore, I believe he would ask Moore, how do we get closer to my capacity limit? And I'm pretty confident that Moore would answer more and more integration. And in the remaining part of this presentation here, we're going to show and discuss how true that in fact is. And we're going to do that by putting a bit on a journey through this network. So we're going to have this bit travel through the network, and as it travels through the network, we're going to see how it benefits from electrophotonic integration. And we're first going to put it through the transport part of the network, which we define as distances from tens of kilometers to thousands of kilometers. We're then going to discuss short-reach applications, which we define as less than 10 kilometers, and typically is gray optics or non-dense WDM optics. And then finally, we're going to discuss how electrophotonic integration can help us getting bits in and out of switches in a power and cost-effective manner. So let's start this journey, and let's start first with the transport part of the network. Let's first discuss some high-level trends in transport. So clearly, transport is becoming coherent. All interfaces in transport today are coherent, and what we are benefiting from coherent is an increase in capacity. We have roughly increased capacity by a factor of 12 by introducing coherent, the factor of 2 coming from adding the extra polarization, and if we use, for example, 64 QAM, we get another factor of 6. So in total, a factor of 12 improvement in capacity. However, we are getting closer to Shannon, so it's becoming more and more difficult to increase capacity and reduce cost by a bit by just going up in constellation size. Once you go beyond 64 QAM, your distance really start to shrink dramatically. So we really left with, from here on, really moving up in baud rate to speak, increase capacity or reduce cost per bit. Another trend we're also seeing is disaggregation, is interoperability. It's putting dense WDM interfaces onto routers and switches, all of which require pluggability or requiring putting optics or coherent into small pluggable form factors. And in order to do that, we need to reduce power and size of the optics, which in turn, of course, drives integration. Coherent is really a ideal application of electrophotonic integration because there are so many optical functions, as you can see to the left. There are high-speed drivers and TAs, high-speed analog and digital converters. There are many high-speed analog interfaces, and there is a very big advanced digital signal processor sitting in that coherent receiver as well. So how can we integrate this coherent transceiver? And there are really two main approaches to that. One is an indium phosphide approach, and the other one is a silicon photonic approach. In indium phosphide, we try to integrate everything but the DSP. In the silicon photonic, we keep the laser aside and try to integrate everything else, including the DSP. And both approaches have pluses and minuses. The indium phosphide have native gain and can eliminate this fiber interconnect between the fiber and the remaining part. The silicon photonic can take advantage of being rather insensitive to temperature, and also since we now can integrate the DSP, we can eliminate high-speed RF interconnects between the DSP and the remaining parts. So each have pluses and minuses, but I believe both have achieved pretty amazing results, and a couple of examples are shown here. One from Finisar to the left, where they have been able to integrate everything inside that green box into a small form factor the size of a quarter. To the right, we at the case have been able to integrate everything but the laser, meaning the DSP and all the optics, onto a common substrate, into a non-hermetic package, also the size of a quarter. But it's clearly look like we all like to compare the size of our parts to a quarter, and I believe it should indicate the size, not the cost of the part. Yeah. So another way of looking at the benefit of electrophotonic integration is by seeing how have we been able to decrease the size of real coherent transceivers over time. What I'm showing here is a very early generation of a coherent transceiver back from 2011 and 12. And as you can see, there are many, many discrete components inside one of these transceivers. You have a lithium niobate modulator, you have external driver, you have a coherent receiver, you have a DSP, and you have an external MUX because we didn't have DACs at that point in time. And also we even have cables going through between some of these components. So a lot of individual parts. Later on, we have been able to integrate many of these functions into much smaller blocks. For example, we've been able to integrate all the optics, the modulator, the drivers, the receiver into a small gold box shown here to the right in that CFP. And also we have been able to integrate the DSP and the electric MUX, which is now becoming a DAC, into a one DSP or one ASIC. And at the same time, taking advantage of moving from 40 nanometer CMOS to 28 nanometer CMOS, so we could shrink the size of that DSP as well. We've taken this one step further, where we now have been able to now integrate the DSP and the optics into one common package. And we are now able to put that into a CFP2 and have it work now at 200 gig, so doubling the speed, halving the size. And if you open up that, or take the lid off that small box, building blocks, you'll see that inside you have a single substrate. On that substrate you have the DSP, and it's sitting next to the optics, which is silicon photonic based coherent receiver, all the modulators and receivers, and you have TIAs and drivers being stacked on top of that silicon photonic die. So 3D stacking. And again, you can see this is about the size of a quarter. And this is really the entire coherent receiver. If you add now an optical power supply, meaning a laser, and an electrical power supply, then you have a complete coherent transceiver working at 200 gig today. And we believe in the near future, we'll be able to put this into an even smaller form factor, a QSFP or OSFP-like form factor, and we also at the same time will be able to double the speed. So putting 400 gig into the same kind of form factors as being used for client optics. And I'd like to point out, this is not just our company working on this, the entire industry is working today on putting 400 gig coherent into these small client form factors. So some of the key trends behind what I just showed. So what I'm showing here to the left is how power, size, and cost have evolved over these many generations. And as you can see, on the per 100 gig basis, and as you can see, we've been able to reduce all these parameters roughly by 30 to 40% year over year, actually beating Moore's law. And if we predict forward, then in 3 or 4 years, the power consumption for per 100 gig for a coherent interface will be actually less than 1 watt. The interesting thing to look at would be how are the relative power consumption between the DSP ASIC and the optics in one of these transceivers. And this is shown to the right. So what you can see here is that actually the power consumption, or relative power consumption, is actually about 50-50%. And this has stayed constant over time. So even in the old days, it was 50%, and today is 50%. And when we move into this 400 gig in a QSFP form factor, it's still going to be 50%. And that's actually quite amazing that the optics has been able to keep up with the ASIC, despite there's no Moore's law for optics. So it actually shows optics engineers in this room are extremely smart. And what they have been doing is providing us with much more efficient optics. They have been co-optimizing drivers and modulators, getting rid of 50 ohm interfaces. They moved from gallium arsenide to silicon germanium type of drivers. And also, very important, and sometimes we forget it, is the control electronic in these ASIC or coherent interfaces takes up a lot of space and are quite costly as well. And what we have been doing is integrating all these discrete components now into a single controlled ASIC as well. So here are some of the key techniques we are using to reduce power, size, cost, and at the same time increase capacity. So Moore's law helps us everywhere, but on the power savings, eliminating interfaces, in particular eliminating 50 ohm interface is key. To reduce size, co-packaging is key. But also, as I discussed before, integrating all the control ICs are quite important. And showing an example here to the lower right, where showing one of our CFP2 form factors, where the red to the left is the discrete implementation we did in the old days. And now by integrating all these discrete ICs into one control ASIC, we have saved 500% in the space, and I believe an equal amount in cost. So cost reduction comes from eliminating separate gold boxes, meaning co-packaging, and also increasing the baud rate. As we double the baud rate, costs don't double at the same time, so we save on a per bit basis. To increase capacity, we need to have even more advanced digital signal processing and also go up in baud rate. So what are some of the future trends we're seeing in electrophotonic integration? Well, one is going to higher and higher baud rates. And here to the right, we have plotted what is the FT for various CMOS processes, both in the past and going forward. And we can see that in 5 nanometer, we're going to have an FT that can actually support A2Ds and DACs that can support 130 gigabaud speeds. So in 5 nanometer, which is going to be available next year, we are actually able to, from an ASIC perspective, support 130 gigabaud. And as you can see from the lower figure, the optics guys are also keeping up, showing that you can actually do 130 gigabaud from the optics as well. So we believe that in a year or two, we're going to see this very high baud rate system coming to market. And of course, very high baud rates require extremely tight, so to speak, integration of both the ASIC and the optics. Another trend or requirement we're seeing is really low cost 100 gigabit coherent interfaces. 100 gig is going to stay around for a very long time, and the new service like on the edge, 5G, as we just heard about, Remote 5 or cable are really driving the need for this very low power, small pluggable coherent interfaces, ideally in a QSFP form factor that consumes less than 4.5 watts. So clearly, electrophotonic integration is going to be key in achieving those targets. Now let's move on to the second part of our journey. Let's move inside the data center. Let's move on to the campus. Let's move in below the 10 kilometers. So here, hyperscalers today are clearly driving the new technology and the speeds. Carriers drove 100 gig, but hyperscalers are clearly driving 400 gig. Clearly, we're seeing a trend towards multi-level PAM4 with digital signal processing at 400 gig. And if you look at some of the, so to speak, key technology behind the electrophotonic integration we are benefiting from in the data center, it's shown here to the right some examples. One is integrating in the optics, in the phosphide, modulators, lasers, and the optical muxes. There's another example here from Luxtera, doing some pioneering work in silicon photonic, and also example of actually monolithic integration of drivers and modulators as well. However, I think the key trend inside data centers and short reach is moving towards multi-level, and truly also believing that coherent eventually will move to shorter and shorter reach as we move up in speed. Not just because coherent adds 4x in capacity, but also because it allows much more efficient equalization, so you can actually live with non-perfect optics as well. And if you look at the complexity, it's very similar to PAM4. The main difference is really between PAM4 and coherent. For PAM4, you need 4 lasers, non-coherent lasers, whereas for the coherent, you need 1 coherent laser. So if you can make this laser similar price as 4 non-coherent lasers, coherent will be quite cost competitive. And we believe also it will be power competitive. We believe you can put 800 gig into a transceiver that consumes less than 80 watts with 5 nanometer CMOS. So as shown here in the lower right figure, as we move up in speed, we predict coherent moving to shorter and shorter distances, and maybe above 800 gig, it might even move inside the data center. All enabled by electrophotonic integration. Let's move to the final part of our journey inside the data center. Let's see how we can help moving bits in and out of switches in a very power and cost-effective way. So let's look at some trends on switches. Switches are getting bigger and bigger, and here to the right there's a roadmap from Broadcom showing that today they're shipping 12.8 terabit switches, soon shipping 25.6 terabit switches. And as these switches get bigger and bigger, to keep the pin count under control, you have to increase the lane speed into these switches. And that creates challenges. You have additional electrical losses when you have these connections running on your PCB, which in turn require more equalization, which in turn increase the power consumption. And the switching functions already consume the majority of the power in the network. So obviously there's a strong interest in how can we reduce the power of moving bits in and out of these switches. And here's an example from Facebook on how their, so to speak, cards look like inside the data center. Shown here, when you go from a switch, typically in their network, to the front panel, you have to go, in some cases, through a connector, and you need to have retimers and gearboxes, which also consume power. So it's actually quite power consuming to move a bit from the switch to the front panel, typically consuming as much as 6 picojoule per bit. Also, if you keep using 400 gig pluggables and put them on the front plate, then beyond 12 and 8 terabits, you now have to move up to 2 rack units. You cannot fit 25 terabit or 50 terabit in a 1 rack unit line card with 400 gig interfaces. You will run out of space on your front plate. So what are the options? Well, there are really 3 options. We can keep doing what we are doing today, meaning putting optics on the front plate and use pluggables, or we can go to onboard optics as shown here in the middle, or we can do co-packaging of the optics and the electrical switch, meaning putting them on a common substrate. An example of that is shown here to the right. It's an example generated by Chris Dorr, showing that you have a 50 terabit switch on a common substrate with 16 chiplets, and each chiplet support up to 3.2 terabit of capacity by supporting 8 400 gig either FR4 or DR4 interfaces. Now, since we are putting these optical interfaces very close to the switch, we can now use a extreme short reach interface consuming significantly less power. Also, you can see these chiplets are sitting in sockets, so they're actually pluggables. Also, you can see actually we are relying on using, so to speak, a laser bank or remote lasers. So we are assuming the lasers are sitting in a, so to speak, a cooler area, and all the lasers are being shared between these various chiplets. Also, you can see from the lower right figure that we have to, so to speak, use very advanced integration technique, including 3D stacking and also requiring true silicon vias on the silicon photonics side to make this happen. So this truly will, so to speak, challenge our integration, so to speak, effort. Now, expanding the view of that chiplet, you can see one of these 3.2 terabit chiplets will contain 4 8-channel TIAs, 4 8-channel drivers sitting on top of the silicon photonic die, which have all the modulators and receivers. And in front of these, you have the 32 LEDs and DACs, including the PAM4 DSP processing needed. Also, since these chiplets are actually pluggable, you could consider some of them being coherent, right? So you could, for example, in some cases, transmit over hundreds of kilometers, and in some other cases, you use the short reach where you go maybe 2 kilometers. So what do we gain from co-packaging of the optics with the switch? Well, let's first take an example of where you, in the old way, where you put the optical pluggables at the front panel, as we're doing today. And let's take an example of a 50 terabit switch, in which case, if you use 400 gig pluggables, you'll need 128 of these pluggables, shown here. And if you calculate the power consumption of the ASIC and the optics and the interface, the total power consumption will be close to a little bit less than 2,000 watts. And it requires a 2-rack unit line card. Now, if you replace that with a co-packaging of the ASIC and the optics, then as shown here by an example from Luxtera, where they are, so to speak, predicting how it will look like if you were to integrate the optics and the switch, then you'll see it easily fit into a 1 rack unit slot. And you also see that because we now get rid of these long interfaces, we also save power on these electronic interfaces. So the net result, the total power, is going to be now 20% smaller than what we saw before. So we save really 100% on the height, and we're going to save another 20% or 50% on power as well. And there's going to be additional power savings from shared lasers and also from shared processors, control of all the PICs in each of these chiplets. And there are also going to be significant cost savings from shared PCB, power regulators, the shared lasers, et cetera, et cetera. So those are the key reasons why the industry today are spending a lot of effort and time on making this come through. So let me bring me on to the final slide of this presentation here, which is kind of a summary slide. So electrophotonic integration has already enabled cost-effective scaling of capacity and density in optical networks, and we believe we'll continue to benefit from smaller CMOS nodes well beyond the 7 nanometer we are in today. Monolithic integration and 3D stacking is in its early phases, but we are already seeing this bringing significant value to coherent interfaces today. It has enabled small pluggable form factors and will continue to enable even smaller form factors as we go forward. As an example, 400 gig in a small QSFP or OCP form factor very soon. Co-packaging of optics and switches is expected to be key for at least 50 terabit and beyond. And also, we didn't cover that today, but there are many other applications where electrophotonic integration can benefit or can help, including OCT, optical coherent tomography, LiDARs. I'm sure we're going to hear in the next talk that also that can benefit enormously from electrophotonic integration. And finally, also, there are some examples of where people are taking a number of silicon modulators, combining with electrical integration, and building basically a key element for deep learning or artificial intelligence. So many applications coming for electrophotonic integration. And that brings me on to the very last slide, which is thank you very much for your kind attention.
Thank you, Benny, for joining us today and for sharing your insights into the future of photonics integration. It's amazing what we are able to do today, and even more amazing to imagine how the future might look like. Good morning, everyone. I am Gabriela Bosco, one of the OFC 2019 General Chairs, and today I'm honored to present the prestigious John Tyndall Award to a colleague and a friend, Kim Roberts. One of the highest honors in our industry, the Tyndall Award recognizes outstanding contributions to fiber optics technology. The award is named after the 19th century scientist John Tyndall, who was the first to demonstrate the phenomenon of internal reflections, and is dedicated to his memory and contributions. The award is co-sponsored by the IEEE Photonics Society and the Optical Society, and supported by Corning. Today, we are recognizing Kim for pioneering contributions to the development of practical coherent communication systems. Let's hear more about his contributions.
It's not enough to be faster. you also need to be better. As a pioneer in electronic signal processing for optical transmission, Kim Roberts has worked on high-capacity fiber optic systems that are now industry gold standard, used by nearly every large network operator on the planet. Growing up in Canada, Kim's childhood was one of creativity and curiosity. The imagination and inventiveness he had then have stayed with him throughout his career, including using his inspired wood pieces to demonstrate theoretical concepts. He studied electronic engineering at the University of British Columbia in Vancouver, while also meeting requirements for an honors math degree. Equally skilled at both calculations and concepts, he's a master of both abstract theory and the gate level of chip design. He pursued a master's degree in a neurological lab, offering homemade pastries to thank his test subjects. Kim then joined Nortel and a team that led to innovations in optics that were truly groundbreaking. The superdecoder method, a key enabler of Nortel's 10 gigabit per second technology, the early optical amplifier program, providing benefits in network economics and ushering in the era of long-haul DWDM optical systems. The 10 gig WaveLogic 1, digitally compensating for the dominant degradation, chromatic dispersion, which many people thought was impossible. In addition, Kim and his team developed the coherent receiver, which allows hundreds of gigabytes of data to be communicated anywhere. Still curious and creative, Kim is one of Ciena's most prolific inventors and holds 160 patents. In his position as Vice President of WaveLogic Science, he energizes top talent to stay in the lead in the race for faster and smarter technology. Kim Roberts sees electronic engineering as a way to bring astonishing ideas to life. His work has been and continues to be essential to the way that our world connects.
Please join me in welcoming the 2019 John Tyndall Award winner, Kim Roberts.
Thank you for this. Well, this award is the most significant individual recognition from our community. We need to remember that developing of cutting-edge fiber systems requires years of dedication from an expert team. So I wish to share this honor with 250 friends back at Ciena. Enjoy your activities today and have a great OFC.
Congratulations again, Kim, for this outstanding achievement. Much of Kim's work has been forward-looking, ahead of its time, and this is exactly what is needed in our industry and academic community. The R&D activities carried out each day by this audience pave the way to the hot topics of tomorrow. From the Internet of Things to 400G to optoelectronic integrations, our work set the stage for future innovations and for a better user experience for customers everywhere. In fact, it was just a few years ago when we were working on ways to achieve 5G, and now we have papers on field trials and demos that mean we are ready to roll it out. And that deployment should play a key role in supporting the needs of our next visionary speaker, Dr. Dmitry Dolgov. Dmitry is currently Chief Technology Officer at Waymo. He was one of the original members of the Google self-driving car project, which became Waymo in 2016. Prior to Waymo, he worked on self-driving cars at Toyota and at Stanford as part of the Stanford's DARPA Urban Challenge team. In 2008, the IEEE Intelligent Systems magazine named Dmitry one of the AI's 10 to watch, the future of AI. Waymo is currently the only company with a fleet of fully self-driving cars on public roads. A suite of sensors, including LiDAR, radar, and cameras, gives Waymo's vehicles a 300-degree view and a detailed 3D picture of the world. Today, Dmitry will be discussing Waymo's mission to make it safe and easy for people and things to move around. Please join me in welcoming Dmitry Dolgov.
Good morning, everyone. Thanks for having me here. Now, the idea of a self-driving car is hardly a new one. In fact, it might be as old as the motor car itself. However, the story of these cars becoming a reality is a fairly new one. So today I'm here to talk about the future of technology, but I'd like to start by revisiting the recent past. Because it was almost exactly 10 years ago, in January 2009, when a small group of us, about a dozen, came together and started the Google self-driving car project. Now, at that time, a small group of students, academics, industry experts had just finished a race of autonomous vehicles called the DARPA Urban Challenge. And I was fortunate to be involved at the time. Now, I gotta say, those early days were pretty amazing. You get to learn about a new problem, and it makes tremendous progress in a very short amount of time. However, while this DARPA-sponsored competition was a tremendous success, it was still incredibly early days in the industry. The technology was in its nascent form. And there was no self-driving car industry to speak of that could push this forward. So fortunately, at that time, Google recognized the transformative nature of this technology and started the project. So when we began, our goal was to take this early research work and take it from the research prototype stage to the next level. And what drove us then, and what still motivates us today, is the fundamental belief that self-driving cars can make our roads safer. Today, worldwide, more than 1.3 million people die on the roads every year. This is an insane number. It's about 150 people whose lives are lost to traffic accidents every hour of every day. This is more than 2 every minute. We can do a lot better than that. Now, we also know that about 94% of the accidents on the roads today are due to human error. People get drunk, people get distracted, people text, and self-driving cars don't. Now, what's more, this technology has the potential to make transportation more accessible for everyone. So when we started this project, in the very first phase of it in 2009, our first order of business was to learn as much as we can about the problem space. So to that end, we created a couple of milestones for ourselves. One was to drive 100,000 miles in total in autonomous mode. And at that time, that was orders of magnitude more than anybody has done at the time. The second milestone was to drive these 10 100-mile routes in full autonomy from the very beginning to the very end with zero human intervention. So here's some videos of those routes. So these routes were very carefully selected to be extra challenging and cover the full complexity of the driving task. You can see we drove at night, we drove during the day, we drove on freeways, we dealt with some construction zones, we dealt with some urban environments. And then, yeah, this is for people who are not from the US, this is a famous or infamous Lombard Street in San Francisco. So at that time, in 2009, we were able to take advantage of the modern developments in sensing technology, compute, and mostly important software algorithms to accomplish these milestones in just under 2 years. And in the process, we developed a better understanding of the problem and the full complexity of the task, but at the same time, we gained confidence to pursue it further, marking the second phase of the project. Now, in this second phase, our goal was to bring this technology to life. And in 2015, we were able to complete the world's first fully self-driving test ride in Austin, Texas. And we did it in a custom-designed vehicle that you see here. It was specifically engineered for this task. In fact, it had no steering wheel or pedals. We called it the Firefly. And the man that you see in this picture is Steve Mann. And what made a trip particularly remarkable is that Steve happens to be blind. Let's be clear, during that ride that he took in 2015, it was a completely uncontrolled environment on public roads. There was no chase vehicle, no police escort, no test driver on board to help out. It was just Steve in a car with no steering wheel or pedals, by himself, taking a ride from a doctor's office to a local park. Now, as Waymo, we're on to our next phase. So building on that second trip of 2015, we've expanded to operate a fleet of self-driving cars in Phoenix, Arizona. And we've been test driving them since 2017 in driverless mode. And today, we have people who are using these cars to get around every day. They take them to work, they take them to school, they use them to run errands. And we've even begun giving some members of the public a chance to experience their first truly driverless rides with no one in the driver's seat. So for these people, what seemed like science fiction a while ago is their reality today. Let's take a look.
Okay, day one of self-driving. Are you ready? Go.
Oh, this is weird.
This is the future.
Yeah, she was like, is there no one driving that car?
I knew it. I was waiting for it.
You'd certainly never know that there wasn't someone driving his car.
Yo, car.
Selfie.
Thank you, car.
Yeah, thank you, car.
So one thing I want to emphasize is that unlike other technology that you might have in your car today, where there's still a driver that is required to take control every once in a while, Waymo is always the driver from beginning to end. And as you can see in this video that we just watched, no one is required to sit in the driver's seat. In fact, there doesn't need to be a person behind the wheel or in the car at all. Now, the Society of Automotive Engineers have developed a scale to distinguish between that. They call them the levels of autonomy from L1 to L5. So levels L1 through L3, there still needs to be a driver in the loop. So these systems are really driver assist ones. But levels 4 and 5 is where it gets interesting. There is a step function, step transition, where you really need to employ the full power of modern AI to completely replace the driver. That means an empty car can come pick you up and letting you travel door to door all the way to your destination while you're just sitting in the passenger seat enjoying the ride. This is truly driverless. And at Waymo, we like to say that our goal is not to build a car. We're building a driver. Our mission is to make it safe and easy for people and things to move around. And we're doing that by building the world's most experienced driver. And while we think that ride-hailing service is a great way to introduce more people to this technology, we also believe that this technology can have transformative impacts across transportation more broadly. You can have a Waymo driver transport goods. You can have them connect people to public transit. Or it can shuttle you around in your own personal vehicle. Now, this is a difficult problem, but we're able to do this to a large extent because at Waymo we have taken an integrated approach to hardware and software development. So rather than, on the hardware side, relying on off-the-shelf modules that might have been designed for something else, our suite of sensors and computers is designed from the ground up specifically for the task of autonomous driving. So let's take our lidars, for example. We've designed 3 types of different lidars for the task of full autonomy. On top of our vehicles, this is the picture you see here, we have our medium and long-range lidar. And give us 360-degree coverage around the vehicle in all directions. Now, our long-range laser is so powerful that it can see up to 300 meters away in high resolution, roughly the length of 3 football fields. Now, down below, around the perimeter of the car, we have 4 short-range lasers. And their intent is to cover the blind spots so that we can detect small objects right next to our vehicle. Now, LiDAR works by painting a precise 3D model of the world around us by sending out millions of laser pulses every second. However, typically, LiDARs have been used mostly just to measure distance to objects. So they measure time of flight, and you get distance to whatever that pulse happened to hit. But because we design our own LiDARs, we're able to extract much richer raw data that can come in very handy in a variety of scenarios, in particular when we're dealing with bad weather. Our vision system is made up of 19 cameras that provide 360-degree coverage of high-resolution color imagery around the vehicle. And because our vehicles operate at all times of day and night, our cameras have high dynamic range that allows them to see a wide variety of lighting conditions, anything from an unlit parking lot in the middle of the night all the way to driving into a blazing sun at sunset. So you may be wondering what's going on in this video. And yeah, while our cameras are pretty high-tech, we do use a fairly low-tech solution to make sure that we're equipped to deal with birds. And this is what's being tested here, cleaning simulated bird poop fairly successfully. There's lots of little things like that that you have to take care of when you are putting a product out there, not just doing research and early development. Now, also on our cars, we have an array of radars. And unlike common automotive radars that you have on many vehicles in the market today, our system has a 360-degree integrated field of view, which allows us to seamlessly track objects all around our vehicle. And the radars also nicely complement the other sensors we have in the car by being highly effective in different weather conditions like rain, fog, or snow. Now, we've designed these powerful sensors to give us lots of rich, raw data so we can use powerful modern AI to do late sensor fusion. Now, this means we need a lot of computational power to chew through all of that in real time. And that's why we designed our own compute platform. So our engineers have put together a computer that's specifically tailored to our needs. It utilizes everything from general-purpose CPUs all the way to custom FPGAs and everything in between. So we get kind of the biggest bang for the buck for our application in terms of watts and dollars. And internally, our engineers like to joke that the computer that we have on the car today compares well to some of the ones that we've seen in the top 500 supercomputer list in recent history. And to give you an idea just how fast compute has been growing on board the vehicle, just in a recent few years, the amount of operations per second that are available to us have grown by about a factor of 50. So that's our main hardware. But we also have some other supplementary sensors in the vehicle, such as microphones that allow us to detect sirens, and cell modems that allow our cars to communicate with one another. And I'll talk a little bit about how they share information later. But driving is a real-time and highly dynamic activity. And because we need to make decisions in real time, and it's a safety-critical environment, all of our vehicle driving decisions are performed on board. So while we don't rely on cell networks to make driving decisions, we can leverage it for expanded capability. So the promise of high bandwidth and low latency networks is something that we're very interested in, and it's very welcome. So we're definitely keeping an eye on the great work that's happening in this field, some of it coming from the people in this very room. Now, when it comes to software, AI touches every part of our system. And to be a capable and safe driver, our cars need to have a deep semantic understanding of the world around them. And today I want to cover three main areas where AI has played a major role in getting our cars the capability to be truly self-driving: perception, prediction, and planning. So first, let's talk about perception. You need to detect and classify objects around us. Kind of the task of seeing the world around you is pretty fundamental to driving around. Second, prediction. We need to interpret the movements of all of those objects, reason about their intent, and predict what they will do in the future. We also need to understand how all of these objects might interact with one another. And finally, planning. Our cars need to use all of that information to act in a smooth, safe, and predictable manner. So let's start with perception. Now, detecting and classifying objects is a key part of driving, but there are many reasons why this can be challenging. So today I want to highlight three main axes of complexity. First, there can be a lot of variability in object appearance. A classic example is people. Now, pedestrians come in all kinds of shapes, postures, and sizes. So here's some examples. On the left, you see some people wearing dinosaur costumes. In the middle, you see somebody carrying a large plank of wood. And on the right side, there's a construction worker that is half occluded by a hole in the ground. So the examples in the middle and the right are particularly interesting because there's a lot of occlusion going on. So there's less data for us to make an accurate classification. But luckily, our high-resolution sensors and lots of data that we can use to train our ML models helps us correctly detect pedestrians in all of these cases. The second axis of complexity that I want to talk about has to do with the environment. Now, environmental factors affect perception because of interference with sensors and reduced visibility. So rain and snow pose challenges, but so do many other factors such as dust or sun glare. Now, the third axis of complexity that I want to talk about today when it comes to perception is context. It's not enough to simply detect and classify an object. Right? Our vehicles need to understand context. This is something that we call scene-level understanding. So let's take a look at this example. There are 4 stop signs. And sure, we can detect each one. But what does each one of them mean? And how should it affect our behavior? So example on the top left, this is your very typical stop sign. It just controls an intersection. We know what to do with that. The example below, there's a stop sign on a school bus. So you have to detect both, and you have to understand the relationships between them so that you can behave accordingly. The example on the top right is a person, a crossing guard, often happens in school zones, that's carrying a stop sign. So we need to understand the situation where this stop sign applies to us, when it's relevant, and other cases where we should filter it out. And this last example on the bottom right is an interesting, pretty rare one, although we actually see this more often than you would think, is a person who is just biking around holding a stop sign. Right? And the right answer there, of course, is just to ignore the stop sign completely. Now, let's talk about prediction next. So we can detect and classify all the relevant objects around us. But we also need to predict what they're going to do in the future. Now, at a basic level, we can do that by understanding the rules of the road, understanding the different road users and their unique behaviors, like pedestrians, cyclists, cars, and then, of course, being able to process real-time information, such as their trajectory and speed. So this works great when people actually follow the rules. But we all know that's not always the case. So here's an example of a red light runner. And unfortunately, we see this kind of thing more often than we'd like. Now, let me break this down from the car's point of view. Our vehicle is about to proceed straight through an intersection. We have a clear green light, and the cross traffic is stopped with a red light. But just as we're about to enter the intersection, all the way in the right corner, we see a vehicle coming fast. Now, our models understand that this is unusual behavior for a vehicle that should be decelerating. So we predict that the car will run the red light. And we preemptively slow it down, which you can see here with this red fence across our path. So this gives the red light runner enough room to pass in front of us while it barely avoids hitting another vehicle. And we can detect this kind of anomaly because we've trained our ML models using millions of real-world examples of real-life interactions. Now, this was an example of just one car doing something anomalous while kind of ignoring everything else that's going on in the world. But driving, of course, is a very social task. So it's important for us to understand how different objects on the road interact with one another. Let's take a look at this video. So here, it's important to understand that as we approach the parked car, that parked car may affect the behavior of other people. In this case, there are 2 cyclists on the right, and we need to anticipate well in advance that these 2 cyclists will want to merge in front of us. Now, let's talk about planning. This last video is interesting, not just because it illustrates the need for accurate perception and prediction models, but also because it highlights the complexity of making decisions. So in this case, there were multiple things that our car could have done. Slowing down was not the only possible decision. So let's go back to that part of the video. Now, as we approach the parked car, there are actually a number of potential moves our car could have made. It could have sped up to pass in front of the cyclists. It could have slowed down to let them in. Or it could have changed lanes to avoid the interaction altogether. Now, in this situation, changing lanes might seem like a good answer, but there's actually a fast-moving vehicle that's approaching from behind. And at that distance and relative speed, that driver probably would not have been too happy with us cutting them off. So part of being a good driver is being able to provide a safe and smooth ride while being predictable to all of those people around us. And the right decision depends on the specifics of each situation, as well as a deep understanding of the social conventions of driving and an understanding of the expectations that other actors in the scene have of your behavior. And with more than 10 million miles of our real-world experience, as well as several billion miles of simulated driving that we can then use to train and validate our AI algorithms, our vehicles are capable of handling all kinds of real and complex situations. Whether it's two dogs going for a midnight run, or a jogger that jumps into the road chasing after her dog, or the hectic weaving of traffic on San Francisco roads, or a crossing guard and a policeman that are controlling an intersection in a school zone. So this is just a very small sampling of things we encounter with our cars operating on public roads. Now, one benefit of having a fleet of self-driving cars is that whatever one car learns, it can pass on to the entire fleet. So this, of course, happens whenever we see something interesting in one car, and then our engineers work on it, they make some improvements, and we push an update to the entire fleet. But it can also happen dynamically with changes to our behavior in real time. So let's take a look at this example. Here, this is in Phoenix, Arizona. You see one of our cars just traveling in the right lane, and it's about to come up on a construction zone. So you'll see this coming into view in just a second. So it's seeing some cones, it's seeing a construction truck, so it does the right thing. It understands the semantics of all those objects, it slows down and changes lanes to the left, passes around it. So all of these decisions are being made in real time by the software on board the vehicle, on the perception, prediction, and planning. Now let's take another look to see how our car is discovering this information. Right? So as these objects come into the field of view, it first doesn't completely understand what's going on, then it builds up the model of the construction zone and understands the exact geometry of it and handles it appropriately. But once it's built up that model of the construction zone, it then shares this information automatically in real time with the entire fleet. So now let's take a look at what happens when another Waymo vehicle turns onto the same road about an hour later. You see that at this time, as soon as our vehicle turns onto the road, it preemptively changes into the left lane. That same morning again, another one of our vehicles, and it's already in the left lane, while other human drivers are forced to slow down and merge at the last second. So you can imagine how handy this kind of capability would be if there was an actual road closure. Our vehicles would be able to take an alternate route without having to run into the same roadblock. Now, today, Waymo vehicles number in the hundreds. But as more autonomous cars join the road, there's an incredible potential for entire fleets of cars to work together and share sensing, prediction, and planning information. And this ability could represent another major leap that will allow us to even better tackle the complexities of real-world driving. For perception, vehicle-to-infrastructure communication could be a wonderful opportunity. One example is traffic lights. So instead of us using cameras to detect their state, they can just share it with us. Or even better, they can share their schedules so we can plan ahead. For prediction, the task of signaling and understanding intent becomes easier if cars can talk to each other and share not just their current state, but also what they're intending to do in the future. And for planning, we can use communication between cars to make our transportation system more efficient. We can reduce the gaps between the cars. Or we can optimize traffic globally in these fleets of cars to reduce traffic congestion. And while advances in artificial intelligence today mean that we're able to build fully self-driving cars and have them on the roads, our goal is to bring this technology to everyone, wherever they are. And there are a lot of exciting developments in the field of communications that could make this technology even more capable, whether we're talking about optical communication and lidars, moving data around in our computers, data processing in the backend and data centers so we can train even more advanced machine learning models, or real-time communication between cars in a fleet that's been deployed. So all of that ultimately means safer roads. So I very much look forward to working more with this community. Thank you.
Thanks, Avicii. I'm not sure what you think, but I think this was really a great and inspiring talk about self-driving cars. I think I'm really keen on getting in one of those cars and try it out myself. And I think one of the applications of 5G we haven't really talked about is probably the premier one in this example, watching HD videos whilst the car is doing the driving for you, right? OK, with this, we have reached the end of our session today. I hope you enjoyed it. We have changed the format a little. I think you have seen it with a little music, lights, and so on. Please give us feedback for next year, what we can do better, what you liked, what you disliked. The exhibit floor is now open. I encourage you all to have a look there, see the latest in optical communications from our exhibitors, and also to enjoy and take advantage of the extensive conference program which we have lined up for you for the next 3 days. Please don't forget to join us for the conference reception at 6:30 tonight, and make plans to visit us again for OFC 2020. Thanks a lot. Have a great day.